Good afternoon, everyone. We'll get started with lecture 5 of Intro to Robotics. So before we get too far into the material, a couple of announcements to make. So the first one is that Lab 2 is due tonight. You were probably already aware of this, but if not, the official due date for Lab 2 is 11:59 p.m. tonight. If you don't anticipate finishing your lab by the time that lab starts tomorrow, I need you to email me as soon as possible just to let me know, because there are some steps that we'll have to take to make sure that the inverse kinematics lab doesn't overlap too much with your work on the odometry lab. So that's absolutely critical for us to work out. So again, if you don't anticipate being able to submit your lab 2 by your lab section time tomorrow, then let me know as soon as possible. Another thing, so something has come up through a bunch of the office hours that we've been running. So if you're using an outside source for help or guidance on your solution to something, put a note in your code that says that you found this outside source and this is what you are using. Some of you have been maybe not super careful. We've had at least 2 cases of people in office hours who have copied code from a previous version of the assignment. So using functions and things like that we don't use anymore, that the only way you would have that exact function and implementation is if you grabbed it from somebody else who's previously taken the class and you've left it in your code while you're sharing your screen. So that's not great, but more importantly, if you do find something out there and you have decided to use it, odds are we already know that it's out there. But if you don't say that you referenced that, or at least use that as a guide, and we find that out, that's just going to be bad, and we don't have time to deal with all that stuff. So if you found something out there, doesn't matter if it's from our class, from some other class, please just reference it. You should be getting into the habit of doing that anyway. Say, especially when we get into path planning, nobody's going to expect you to say implement Dijkstra's algorithm from memory or from some loose definition that a slide has given you. So you're going to probably look on Wikipedia. That is encouraged, and that's totally fine. Just cite your sources. So if anybody has any questions about that, you can send me a private message in chat, or we can follow up after class today. Okay, so homework 1 is out and it's due on Friday. Hopefully you've had a chance to at least look over the questions and figure out where maybe some of the gaps in knowledge are from the lectures to actually applying some of that stuff. There's heavy overlap with the skills that you needed to complete the odometry lab, so hopefully it's not all totally new, but if you found some of the question wording unclear or you have just other questions in general, please post on Piazza. We are happy to help you all week with that. Some people have emailed in asking if handwritten homework is okay for this, especially for maybe some of the more mathy parts of the homework. That's fine. You can just take a photo of it and then insert that into your document and then upload that. So that's okay with us. Just try hard to make sure that it's legible. And then the last bit of homework thing is that future homeworks are going to be Python coding exercises. So this will probably be the last one that you actually have to do this kind of written out mathematical derivation stuff. So look forward to more Python implementation exercises and less derivations and solving math equations. So before we move on, does anybody have any questions about Lab 2, Homework 1, things moving forward? Okay, sounds good. All right, so we will move right on. So here is our roadmap of where we're at. So we have finished dealing with most of our basics. So we understand how to move robots around. Now with the odometry lab, we can track where they're going. After today's inverse kinematics lecture, we're going to be able to build feedback controllers that tell robots how to get to places that we want them to go. So we're going to continue talking about manipulator arms, separate from mobile robots. We're going to cover both cases. For our purposes, we care a little bit more about the mobile robot case. And that gets a little bit interesting for us Oh, should the basis vectors for a coordinate system all be the same magnitude? So if you're referring to the question for homework 1, no, you can just put a unit length vector for that. So we said in the question, like, hey, just so you know, these are not unit length. We left them not unit length because we figured it would be easier for you to come up with that third vector. So the answer that you provide should be unit length, but you don't have to make it the same as the others, for example. And you don't have to normalize the other two that are there. Okay, great. So today we're talking about inverse kinematics and feedback controllers. And so just as a very quick whirlwind recap of our forward kinematics and our introduction to this material, right? So we've been talking about essentially going through this transformation. So going from a configuration in joint space. So I picked my motor angles and then getting out some kind of location in the real world or Cartesian space. And now we're talking about, I've got some location in Cartesian space, and I want to get back to some kind of joint configuration for my robot. And one of the most helpful tricks that we've used for figuring out that transformation is going between coordinate frames, right? So if we understand that we can represent our robot as having a coordinate frame at its base here, and then another coordinate frame at the end of its first link here, and then maybe even another coordinate frame at its end effector, then that's going to help us figure out where things are in the world, and then we can use that to figure out how to get to those positions. So the way that we were transforming between coordinate frames is with something called the homogeneous transform. So this is something you've had to implement or at least utilize in homework 1. And I wanted to bring this slide up again just to show that, like a quick reminder, that whenever we see notation that looks like this, what we're going to see is a couple of variables that have lengths that are different or sizes that are different. So for example, so QA here is a vector. So that could be our X and our Y, or it could be X, Y, theta. That's really just up to us to declare. So there's at least one problem on the homework where you have the freedom to choose if you want to represent X and Y or X, Y, and theta in our vectors Q over here. This vector P is also something that we would consider X, Y, or X, Y, and theta. And so this matrix in the middle is going to have a different size depending on what dimensionality of problem we're trying to solve. So this rotation matrix, if we're just talking about, say, the 2D case, it's going to be a 2x2 matrix. So we'll have a cosine theta, negative sine theta, and then a sine theta and a cosine theta. And so we'll have a 3x3 total matrix for that. If it's a 3D rotation, then R will be a 3x3. And that's going to mean that our whole matrix here is 4x4. So the important thing to note is that this is always going to be square in the middle here, and that's going to have to match up with the size of our vectors Q. So just to make that extremely concrete and to match one of the problems that we have in homework 1, here is an example of the homogeneous transform matrix. So this is a 2D rotation around, so like this is the same rotation matrix that we would have if we were just rotating on the 2D plane, but I've included the third axis here. So this is the same thing as the 2D rotation. I'm just being explicit and saying I'm rotating around my Z axis. And so now my rotation matrix is a 3x3. And I've also said that my vector, my points are going to be 3 lengths. So I'm going to have my X, my Y, and my theta in there. So that also means that Q is going to have an X, a Y, and a theta, just like it has down here. So do you have any questions about setting up the homogeneous transform, or maybe even just what's going on with this? Why is T theta in the last column? Isn't the right column just the translation? Yes, so you can think of it as an offset, right? And so whether it's theta or it's Z or it's something else, it's still just an offset. And so in one of the homework questions, the starting axis that you're working with has an offset already. So if we're looking at the problem where you're tracking the robot, the robot's at some angle, and then the robot finds some object, and that object is at some other angle in a different coordinate frame, then doing this is going to, essentially, if we work it out, right? So everything in the last column here is going to get multiplied by this 1 and added on to our answer. So when we get to the angle, it will be 0, 0, and then QB theta plus T of theta, because T theta is going to hit that one there. So it's just adding those two angles together. So that's what's going on there. Good question. So likewise, if we wanted to add even more variables onto this, we would just keep adding like another identity row and column in here, right? So we'd have 0, 0, 0, 1. These would all be zeros. And then we'd have another one where our tx, ty, t theta, maybe some other variable was, and then a 1, and then all zeros. So that's how we just increase the size of this homogeneous transform to accommodate larger and larger vectors. Okay, so moving on from here to odometry, right? So actually keeping track of where everything is going. So hopefully this last kind of overview of odometry makes the most sense, because now you've actually had to implement it on a robot. And so what we're looking at is things from the robot's perspective. So here's our robot. The robot has an x-axis always coming out of the direct front of the robot. So the robot's pointing this way. And then there's a y-axis, which is orthogonal 90 degrees to the left of that x-axis. And so we can compute the change in position along the x-axis based on our wheel position. So this is our displacement over, say, one time step. And so that's going to just be the average of how far my two wheels have moved, right? Because this is a rigid body. So we keep the middle in between the wheels all the time. So it makes sense that the center will still be at the average position of the two wheels. This robot does not drift sideways, so there's never going to be a y component to that. And then lastly, the amount of rotation that I experience is the difference between how far my right wheel has moved and my left wheel has moved, divided by the distance between my two wheels. So this is from the robot's perspective, right? How far I've moved, how far I've turned. So if we wanted to put this in terms of some inertial frame, right? So this axis out, set of axes out here, then I just need to relate those local translations and rotations that the robot has made back into this other coordinate frame. And so I can say that the x and the y offset, right, from that that last movement is going to be the x component and y component of my robot's motion. So here we have x.I is the x component of my robot's displacement minus the y component of my robot's displacement. So we knew that this one was 0, so we don't have to worry about that. So it's just the x component. So project that x.r vector onto the x-axis for my x displacement, and then my y displacement in the inertial frame is just the y component of that. So we're essentially just attributing portions of x.r to each of my axes using sine and cos here. And because our rotation axis lines up, there's no translation or anything or transform that has to happen there. The rotation that my robot experiences is the same one that I would see in my inertial frame. And so we wrote it out this way as a more compact representation, but this is the same thing as this. And so you've hopefully implemented all of this by now. And the key insight here is that if we can figure out basically how far your robot has moved over the last piece of time that's gone by, so in this case, one sim time step, then we can just add those up over time and we figure out where our robot's gone. So that sums up where we've gotten so far. All right, so now we can track where our robot is going. And it turns out that's really handy. We can use that for a lot of stuff, and we're going to. But this method is also prone to a lot of error. And so we've come up with at least one way now to bound that error. So if we know something about a landmark from our sensor readings in the environment, we can use that to reset our pose to something that we know. So in this case, we used the start line, and that's going to bound the error so that you have a maximum error no matter how many laps around the course you do. All right, so we've covered all of that. And now we moved on to inverse kinematics. And last time we motivated with this problem, right? So we have some trajectory, or at least some path. The difference there being in a trajectory, we typically care about timing information versus a path just consists of a bunch of points. And so we want to be able to define a trajectory in our end effector space so that we can then convert it to something in our joint space to actually realize it. So if I know where my end effector is going to be at each time step, then I should be able to figure out what my joints should be at in order to complete that path in practice. And so we started covering how the inverse kinematics for a manipulator, something that is anchored and holonomic, is going to be different from something that is not anchored to the ground. And so in the manipulator case, we are given some point that we want our end effector to be on. So for this 2D manipulator, we care about x, y, theta. And what we'd like to get back is Q1 and Q2, which are the angles of each of the motors of that arm. For the epoch, right, we're going to give it an x, y, theta location, so some point on the plane with a direction, because epoch is orientable. And we want to know phi L and phi R, which is how much I should turn each of my wheels to get there. But because it matters which order I do those rotations in, right? So if I just did all my left wheel turns and then I just did all my right wheel turns, I'm not going to get to the place that I probably wanted to. And so because of that, we can't just directly apply inverse kinematics equations to get our wheeled vehicles to get where we want. And there's a more lengthy explanation of all of this stuff in the book. So you'll see some of these pointers throughout the slide deck. So for manipulator arms, we can end up with redundant solutions. And redundancy is something we've talked about a little bit at this point. So when we work out the actual equations, you're going to find that you have multiple solutions, and that's fine. That's something that's good for us, right? Because it gives us more opportunities to get to a valid configuration. But it also means that it's a little bit harder for us to arrive at those solutions, right? Because now we're not necessarily going to have like X equations, X unknowns, and it's not always going to be solvable all the time. So towards the end of last lecture, we look at this example of end effector position control that we could use, say, using an inverse kinematics controller. So what's happening in this demo is that the X, Y, Z position of this little ball is being reported back to the software, which is then running it through an inverse kinematics function to get joint angles for the robot. And then the robot is just interpolating to those points. And so we might run into trouble though. If you need this video about IK, I post the slides after each lecture. And so I think this slide is also in the slides for last lecture, which I posted earlier today. So if the ball here gets too far away from the robot arm, then interpolation is probably not a great strategy for me. Maybe because I can do some bad stuff with my robot, right? I can self-collide or I could hit some joint limits. But either way, we still have this original problem of maybe I have some high degree of freedom system and I don't have an analytic solution to it. So we introduced this optimization problem. So I can define some kind of error surface here. So I'll have a current state of my robot or my end effector, some XY, and then I'll have some desired state. And this surface that's plotted is maybe the distance of the end effector from that desired state. And then my axes here are just my motor positions. Right? So if I just compute that distance value for every possible motor configuration, then I should be able to figure out where the minimum is. And then I could just send my robot arm straight to that minimum. So in this case, our error signal, it would just be the distance. So I could use my forward kinematics, right? So given an alpha and a beta, so angles of my robot arm here, I could just figure out where is the end effector, pass it into this Euclidean distance function, and then figure out how far away I am. And then I just pick the value that is the smallest error and I'm good to go. So if I wanted to get my robot from one of these spots to the other, I could just linearly interpolate between the position of my current state and of the desired state, or I could follow my error surface, right? I could just kind of roll downhill, which raises this question, because it's unlikely that we're going to actually compute this full surface at any given point in time. And that's going to be somewhat expensive. And surely we don't need to know about all of these areas over here or over here in order to get to a satisfactory answer. And so we discussed briefly these optimization-based solutions. So we won't have an analytical solution available most of the time. That's just how it works in robotics. Our problems are too hard for that. The good news is that optimization methods don't require a whole lot of input from us in terms of specialization for the parameter space or the domain, because they're just general methods. But we still do have to set up the problem properly. And so when we're talking about strategies, right? So if we keep in mind that plot on the previous slide of the error surface here, we want to figure out a strategy that's going to allow us to get from this spot down to this spot without having to have fully plotted out this surface, right? So we don't really know what the surface looks like. It is defined everywhere, but we don't want to do all of the work. So the one strategy that we have for doing that we talked about was coordinate descent. So I'm going to pick one axis at a time. So I'll pick one motor at a time, and then I'll try a bunch of different values for it. That minimizes my error, right? I keep the one that minimized it, and then I move on to the next motor, and I try to find the value there that minimizes the error signal. And so this is called coordinate descent. And coordinate descent has a nice guarantee that my solution will never get worse, right? So no matter how many times I run this, I know that I won't get further away from my goal, but I'm not necessarily guaranteed to actually get to my goal. And so for this plot that I showed last week, we don't need to actually have this full surface rendered, right? We don't actually need to know what these values are. All we're going to see is basically where we currently are along this path here. So when I'm evaluating how far do I tune, say, this motor, right? I'll probably get somewhere over here before I decide, nope, this was the minimum value, but I don't have to actually evaluate this whole surface. And so this solution of just tweaking one parameter at a time, right? Moving one motor at a time makes sense intuitively, but it does run into trouble because axis aligned movements might increase the loss function for a surface that looks like this, right? So we could get unlucky. And so the thing that we ended on was generalizing this idea of coordinate descent. So instead of just doing one motor at a time and trying to figure out like freezing the other ones, moving this one until I hit some minima, and then moving on to my next motor in line, I could just try to move all of them at the same time, right? So if I knew the direction of steepest descent, well, then I can move both of my motors, or however many I have, in that direction, and I'll just stop when I hit some minimum. And so here I show this optimization scheme for fitting a line. And so here we have the two parameters of our model. But again, this could also just be the alpha and the beta angle of my manipulator arm. And I'm just moving along the gradient, right? So I've taken the slope essentially of my error function, and I'm going in the direction that minimizes it. And here we can see the line rendered for each point on this graph, right? And so the idea is that I'm constantly moving into a better and better fit. Does this necessarily mean that I'm going to hit an optimal fit? No, right? If my surface is non-convex, meaning that I have local minima, so like a small bowl maybe that is above the actual true minimum, I won't be able to overcome that. I'm going to find that bottom of that local minima and I'm going to stop there. But this is a pretty good start. So that brings us to our new material, right? So we've talked about a couple of different solutions for this optimization problem, but now we're going to get into a bit more detail of why this works. So finding the position for IK, right? So we're given some end effector pose that we want, and now we want to find the joint angles that will get us there, can be framed as a minimization problem. And so this is just part of an umbrella of optimization methods, but today we're going to talk about unconstrained minimization. And so unconstrained minimization is any problem of this form. So you are given some function, f of x, let's say, and so in this case, f of x could be the distance of motor configuration x from the ideal configuration. So f of x is the distance between the forward kinematics solution for motor configuration x, so like where my end effector is for some motor configuration I choose, away from where I actually want my hand or my end effector to be. So this says that I get control over what that x is, right? So I want to find the joint configuration that minimizes this error function. And so usually in this case, our x is just some real valued vector. So that could just be one entry for each of my motor joints. Now, in order to figure out if we've solved this problem, right, we need to have two things, right, at least to figure out if we're at a local minimum. And so for one of those is that our gradient has to be 0, right? So if I take the derivative of my function at that point, my slope should be 0. So great question in the chat. How is this distance even figured out? If the robot knew the distance away, wouldn't it be able to just fix itself? So the distance is in end effector space, right? And so there's some non-trivial mapping between our joint configuration, right? So what angles each of my arm motors are, for example, and the end effector position. So the Cartesian coordinates of the hand. So it's not really clear how changing my motor angles is going to actually get my hand closer to where I want it to be. So in this case, if x is a list of joint values, then I need the forward kinematics solution of that. And then as I change x, right, that's going to change where the Cartesian coordinates are. and I have an error signal there, right, from the desired XYZ position, let's say, of the hand. But there's not a straightforward relationship between those. So the robot doesn't actually say like have the answer in the coordinate system that it needs, right? The robot needs the answer in terms of joint angles. So if we have this, right, this error function, so again, like for any single proposed joint configuration, I can just run forward kinematics and figure out where the hand is. And so then I can figure out the distance between that position and the position I want the hand at. But I still have to generate these potential joint configurations. So to be at a local minimum, right? So if I'm trying to minimize that error, then the gradient of that function with respect to x, let's say my joint configuration, has to be 0, right? So there has to be no slope. Because if there were a slope, I could just follow that downhill and get to an even better situation. But there's one other condition that I need to know to ensure that I'm actually at one of my minima. And that's that my second derivative has to be non-negative. And so if we remember back to our calculus days, intuitively what that means is that the place where I'm at in my function is going to be flat, right? So that's what this first one is saying. And this one is saying that my function is generally bowl-shaped, right, curving up. So that means that not only am I at a flat part, but also the things around me are going to be curving up. Because if they were curving down, then that suggests that there's more minimal answers than the one I have. So this is one way that we operationalize calculus in order to figure out, do we have a good solution to this problem or not, right? And so figuring out an inverse kinematic solution is a very practical minimization problem for us to solve. So if we're talking about using gradient descent, then it's important for us to also talk about the assumptions that we are making about our problem. So in particular, we don't really have an unconstrained minimization problem. There are constraints on this, but even still, even ignoring things like joint angles and like feasible robot configurations, we still need to have some set of assumptions about the function that we're optimizing over, right? If we're going to say we want to get the best answer out of this, then we're going to have to make some claims about what that function looks like. And so in particular, if we're going to do something like gradient descent, right, where we're just following the hill down to the bottom, then we're implicitly assuming that our function is convex. And so convex functions look like this. So convex functions are generally bowl-shaped like this. And the technical criteria that we have for something to be convex is that you can draw a line between any 2 points on that function. So this bowl-shaped thing is our function. And then this line cutting through it is the test line that we're going to use. And if I draw a line between any 2 points on my function, then I will know that my function is actually less than or equal to that line, right, for any 2 points that I pick. So that essentially guarantees us that we don't have anything like kind of wobbling up here, right, which would imply that there are local minima as opposed to just one global minima for us. And this math down here is just saying that as I interpolate from point x1 to point x2 on my original function, that's always going to be less than or equal to the line that connects point x1 up here to point x2 over here. So that's just the formal definition of a convex function. And so if we assume that we have a convex function, then our goal is to find this bottom point. The way that we can find this bottom point, as we've discussed, is through something like gradient descent. And sort of more generally, this is just an approach called steepest descent, where we would initialize our answer, right? So we're going to try to find the x coordinate that minimizes this. So here might be our x-axis, and then this is f of x. And so what we need to do is we initialize to some initial point. So let's say that we're here at x equals 0 right now. And in robotics, we usually don't get to initialize x to some random guess. We usually want to initialize it to the place that we currently are. So that's one thing that might be a little bit easier here. But either way, we have some initial estimate for x. So let's say that's the current joint configuration of our robot arm. My goal is to figure out which direction do I move, say, my joints to minimize my error, right? So the steepest downward direction for my error function, which might be this bowl-shaped thing here. So if I take the derivative at my current position, then I get the slope, right? So I get this linear approximation of my function at this current point. And then I can just follow that downwards, right? That's going to tell me which way is up, which way is down. So I can just follow that down. So I will find the steepest direction, so delta x. I will pick how far I want to move in that direction. And there are a bunch of choices that you can make there. And then I just update my x coordinate. So here is my original x plus the direction I'm moving multiplied by some step size, right? And so I can solve for that lambda, or I can have it something fixed and just iterate over this loop multiple times. That's up to us. Any questions about the setup so far?
Will we be dealing with like continuous functions, or will they be like discrete and we'll have to like just kind of guess in a circle, like where the steepest descent is?
So is the question about continuous versus discrete about like whether or not you'll have like a gradient to follow, or?
Like the function that we're finding the gradient of, will we have like a defined function, or will it be more like we're just like guessing points and finding around us where the steepest gradient would be?
Great question. So the question is, do we have this function in analytic form? Right. So if I have it in analytic form, so like I'll have some like written out equation, I can then presumably just take the gradient and maybe find a solution to it, set the gradient equal to 0 and do, you know, my normal calculus thing. We won't always have that. And so because we won't always have that, it turns out that's okay because we can empirically measure the gradient around us. And so one way to do that is, just like you said, so pick some points really close to where we are, and then calculate the difference, right, in our function. Because that's really what the gradient is doing. Like the derivative is just finding, you know, the f of x plus some tiny amount minus f of x divided by that tiny amount. So if we go back to like the limit definition of the derivative, then, you know, we can just do that empirically. We don't actually have to go through the full solution for it.
Thank you.
Cool. So let's work through an example of this. So gradient descent for solving inverse kinematics, and we're going to do it on this 2-link robot arm that we've been talking about. And then after this, we're going to move on to our mobile robot. So the things that we're going to assume: we have a distance from goal function f and motors alpha and beta, right? And so our distance function is going to be parameterized by our alpha and our beta. Because like essentially what we're doing is we're going to find the end effector's position. So we're going to find, let's say I want my end effector to be over here where the laser pointer is, and it's currently where it is over there. So my alpha and beta look like the picture there. So my error function is going to be the distance between the current end effector position and where that laser pointer is. And so for any alpha and beta I give it, I want that distance, right? Distance between the forward kinematic solution and the laser pointer dot. So I can frame that this way, right? So the gradient of my error function, right? So the distance from my goal, which depends on my motor angles, is just going to be equal to the derivative with respect to alpha of that function and the derivative with respect to beta of that function. And if we remember like what that actually kind of means in terms of our objective, if I find f, our error function, if I find the derivative with respect to alpha, I'm learning the relationship between how changes in alpha change my error function result. So I can figure out like which direction do I have to turn alpha in order to minimize that. Likewise, if I take the derivative of my error function with respect to beta, right, so the beta motor, then I'm learning how changes in my beta motor are going to increase or decrease my distance function or my error function here. And so here is our definition of our derivative, right? So like the limit of this as delta alpha goes to 0, that is our gradient. That's just our definition from calculus. And so what we're doing is we're trying to figure out how small changes in alpha are going to affect my error signal and how small changes in beta affect my error signal. Is anybody unclear on this concept so far? I recognize it may have been a long time since some of you have seen calculus or had to think about it, and now it's all kind of coming crashing back. But I would encourage you, if you are even a little bit lost, to send me a private message in chat just so I can modulate the flow of lecture to make sure I don't leave anyone behind.
I have a quick question.
Sure.
So to minimize the error here would be to like turn the motors at the minimal amount to get to your goals like state. Is that, am I understanding that correct?
Yeah, well, so the solution with the minimum amount of error signal is going to be the one that gets the end effector like as close as possible to the goal location. And so in this case, there's no notion of distance, right? So like distance of like alpha and a beta, right? So it's not like my new alpha and my new beta should be close to the one I start with, just because like I'm just trying to find any amount of solutions. So if I have multiple solutions and there's a close one and a far one, they'll be treated equally good in this case.
Okay.
So the idea, right, overall, is that I just want to figure out which way do I turn each of my motors to reduce my error signal. And my error signal is just how far away I am from where I want it to be. So I can take this derivative and that will tell me that, right? It'll give me the slope of that function that says, okay, if you increase, say, your alpha variable, then it's going to reduce your error signal, right? So in this case, if my goal location was over here, then really any reduction in alpha and any reduction in beta is going to bring the end effector closer to that laser pointer dot.
I have one more. Oh, I'm
yeah,
sorry.
go for it.
My second question. So this error is coming from like the like uncertainty in like the motors, or the error from.
We've defined the error. So the error is just the Euclidean distance between whatever the forward kinematics solution is for my motor configuration that I'm picking and this goal point.
Okay.
So like you get to pick a random joint configuration, and then we figure out, okay, where does that put your end effector? And then how far away is that from this this red dot? That's your error function.
Okay.
So when that's
sounds good,
you know, we've got to where we want to be.
Okay, that makes sense.
Cool. Okay, so we've figured out now with this a relationship between changes in our motor position and getting closer or further away from our goal. And so now we need an update rule, right? We need to figure out, how do I change my alpha and my beta motor here? Like, how do I actually figure out what to set those to? So here I still have my gradient definition from the last slide, and I just have one example. This is the derivative with respect to alpha. But if I want to actually update my motor, then I don't want to do it all at once. So if we remember, we have that bowl-shaped function, and we're trying to get to the bottom of it, but we might not be able to just come up with like a one-step solution for that, right? So if I just picked a fixed distance to move, I might overshoot the minimum. And so one way that you can do this with gradient descent is to take your current motor position and then go some small step size. We're going to call it L, like we can call it a learning rate. We call it a step size, doesn't really matter, it's the same idea, to scale how far in the direction of the gradient that we were going to go, right? So this delta F alpha is just saying the gradient with respect to my alpha motor angle. So I want to go in the way that minimizes that. So that tells me the direction to go. And this L is something that I will choose to figure out how far in that direction to go. So this is just saying like we're going to do it a little bit at a time. So we're not going to just take one giant update. We're going to move a little bit in that direction, reassess, recompute our derivatives, right? Because our slope might have changed, and just keep progressing in that way. And so if we do this enough times, every single time we're guaranteed to at least not get worse, and we'll just kind of follow down the hill until we hit that minimum, or at least very close to it, depending on our stopping criteria. So this is just saying take a gradual approach. Okay, so let's make it, let's see, is lambda from the previous slides the same thing as L? It absolutely is, yes. So lambda, the step size from the steepest descent slide, is the same thing as the L here. It's just some kind of scale factor. And there are more or less complicated ways of picking a scale factor. Pretty much the easiest thing to do is to just choose a small number, and then you'll just have a lot of iterations of this process. But as long as that's not computationally limiting for you, that should work just fine. Okay, let's relate this though back to our actual two-link robot arm. So we have an equation for the forward kinematics. And so we're going to want to like have some kind of model, right? That's going to tell us, hey, if I move my alpha motor and my beta motor in a certain way, what is that going to do to the X position and the Y position of the hand at the end of it? So we can set it up pretty much the same way here. So I'll slowly walk through this, but again, I encourage you, send a private message if you get lost or if you have any questions. I'm happy to stop and slow down and go through it, just because different people are going to be coming into this with different levels of background knowledge on this topic. So this is just the forward kinematics equations that we covered a couple of lectures ago. So here we have alpha, our first motor, and beta is our second motor. L1 is the length of my first robot link, and L2 is the length of my second robot link. And so for some motor configuration, alpha comma beta, the X position of my end effector is just equal to this, L1 cosine of alpha plus L2 cosine of alpha plus beta. And similarly for the Y position of our end effector. So given alpha and beta, I can run these forward kinematics equations and figure out exactly where this is in space. And so I might care about things like moving my end effector around in Cartesian space, right? That would be much more convenient for me, right? I can much more easily kind of intuit my way through this of, hey, if I want to get the hand over to here, I might just tell it, hey, move the hand directly to the right, like move it along the X-axis, right? And keep the Y-axis value to be the same. So if I were to do that in joint space, that could be somewhat difficult, right? Because there's not a clear relationship for doing that planning here. But I can use the gradient to figure out how changes in one affect changes in the other one. And so that's what this line is showing. So I'll walk through this. So this is a function, right? So I plug in my motor angles and it tells me the X position of my end effector. So if I take the derivative of that with respect to alpha, I'm saying, how does the X position of my end effector change as I change the position of this motor alpha? And then likewise, I want to know, how does the X position of my end effector change as I change beta? So I take the derivative with respect to beta. And the reason I'm multiplying by delta alpha and delta beta is because that's the amount of motor turn that I want to happen on both of those, right? So now I can say that the change in my X position is equal to, well, whatever this is, multiplied by how much I've turned alpha, plus whatever this is, multiplied by how much I've turned beta. So now I have at least like a relationship. So I know for some proposed shift in my motor rotations, what my change in X is going to look like. And I can do the exact same thing for the Y position. Right, so if I change my alpha motor by itself, then presumably the Y and the X position of my end effector is going to change. Now, if I wanted to figure out a way to change alpha while not actually changing the Y position of my robot, I can figure out some offsetting value of beta, right? So I can figure out whatever amount of alpha I want to move it, I can find an amount of beta that makes this 0. So if I did that, then the Y position of my hand is not going to change, right? So like as alpha decreases, maybe beta will increase for some amount of time. So I have this relationship now between position and angle change, right? So between end effector space and joint configuration space. And I can express this in a more matrix multiplication-esque way. So I'm going to take these 4 derivatives, and I'm just going to stick them into this matrix here. And so we call that the Jacobian. So again, if you remember from calculus, the matrix of partial derivatives, right, first derivatives, is called the Jacobian. And so my rows are going to be X and Y, and my columns are going to be taking the derivative with respect to alpha or with respect to beta. Right, so I have every combination of variables here. And if I multiply that by this Q dot, which is just delta alpha or delta beta, then I get the relationship between change in position and change in my robot's configuration space. Okay, so in the chat, somebody messaged me like, is this really like a kind of like a brute force method to figure out how to get to my goal state? So if my goal state, let's say, was to move my end effector over here, then like, is there a more efficient way to do that? And so if I actually follow the gradient, then this is a fairly efficient way for me to do it because I'm not actually randomly guessing or checking anything. All of these equations that we're setting up are going to be things that we plug in to that gradient descent. So it will tell us what our next check is. So we're not actually going to be kind of randomly throwing out guesses. We're saying, I'm right here. What change can I make to get closer to my goal? And so you might be able to think of it as like a potential field, or even better, just if you have some kind of surface, we're just rolling downhill. And the only things that we're going to check are the things along our hill, along the path on the hill that we're taking. So we don't have to look at, say, the rest of that topography at all. Is this an alternative to PID or control law? So this is not an alternative to it. In fact, you would probably use these in your control law. And that's actually something that we will talk about in just a couple of slides. Okay. So again, going with this theme of like, let's actually run through our example and not leave this very abstract at all. So I'm going to take the stuff from the previous slide and I'm just plugging things into it. So none of this is new. It's just taking the equations up here. So we have X position of my end effector and Y position of my end effector. And I'm taking the derivative with respect to alpha, right? So this is d alpha of x e parameterized by my motor positions. And so I just run through the derivative. You don't have to remember that. No one's counting on you to memorize your derivation rules at this point. You can look them up if you need them, but these are the equations that we get back out. So these are the entries for my Jacobian. So if I think back to my relationships here that map changes in my motor position to changes in my end effector position, then I would just plug in these results into these entries of my Jacobian. And then I could figure out how my position will change as I change the joint angles of my robot. Now, usually what I want to do is the opposite, right? I want to know how changes in position are going to like result in desired changes to my joint configuration. So if I say, hey, I want to move my hand 2 units to the positive X direction, I want to know what delta Q or Q dot, like what change in my motor configuration I should have for that. So I can change this equation around just by multiplying each side on the left by the inverse of the Jacobian, right? So if I do J inverse on the left side of here, it cancels out. And so I just get Q dot. And then so that J inverse will be over here multiplied by my desired change in position, delta XE and delta YE. So then I can say, all right, multiply my inverse Jacobian by wherever I want my hand to move. So like 2 units on the positive X axis. And that's going to tell me what I need to change in my joints to actually achieve that. And so that is something that we will be implementing in our next lab. Okay, so we have a fairly robust theoretical background now for what we're trying to do, at least. Right? We wanted to map this change in position back to changes in my robot joint angle and vice versa. So now I understand how to freely kind of go back and forth between those coordinate systems. But nothing is really that easy in practice. So we have a couple of problems that could crop up. So let's try to diagnose them and figure out what could cause this to happen. So here are the equations, right, that we're going to do that we have solved. So I'm trying to get to some joint location. So here's where the target position is, that ball. And here's my gradient with respect to my first motor, let's say. And then here's my update equation. So I'm going to update my first motor by its current position minus some step size multiplied by the direction that reduces my error. So what could be causing this kind of jittery behavior to be happening?
It's constantly overshooting, like going back and forth.
Yeah, so if we think about this as a function, then maybe my error function looks something like this. And I'm constantly jumping between this position and this position on my loss function. And so that's because my step size is too big. If the step size were smaller, I'd be able to get actually down to the true minimum. Okay. What two parameters, so we talked about the step size, so the learning rate here. What other parameter could be causing some kind of problem with this estimate?
Maybe if you can't calculate the inverse of your Jacobian.
Okay, yeah, so there are definitely like numeric issues that can come up. Like maybe I've asked for just a position that the robot can't even get to, right? And so there is no convex guarantee that's able to hold for that, like for the actual like achievable space. Okay, let's also look at some other problems that might come up. So I can go down this error surface, right? But if I don't actually account for the physical reality of my robot, I could end up in some trouble. So how do we fix this? We can give limits on the joint angles, right? So we can say that if we're doing an update, then we don't allow the joint angles to go past the tolerances of our robot. And this can get somewhat tricky, especially with self collisions, in addition to, say, like the joint angle limitations of the robot. Okay, so what cool stuff can we do if we've suffered through all of this? Well, it turns out if you can find an optimization-based approach to inverse kinematics and solve these problems fast enough, then that means that you can get your robot to go to a desired place fast enough to do stuff like that. So what's happening here, right, is that there's a motion capture system around it that's tracking the robot hand and these objects that are being thrown. And the software is modeling, right, the parabolic trajectory of these objects that are being thrown. And then the robot's picking an intercept point and then solving the inverse kinematics problem to figure out what its joint angles have to be to get the hand into that intersection point. And so the result of that is it looks like this robot is really great at catching stuff that you throw at it. So this is sort of one of these far off capabilities, but you have all the building blocks for it. And so we'll keep talking through kind of like supporting infrastructure for doing stuff like this. But I encourage you to start thinking about like, wait a minute, if I have the ability to get my robot to move to a point in space, like what can I really do with that? And the answer is a whole lot. And so the motion capture camera here is used because computer vision is not so good at localizing objects at this kind of frame rate necessary. So we just sidestep all of that, and it just gives ground truth posed for each of the objects in the scene.
Hey, Brad, with the learning step size that you're talking about and how you can decrease it to find the minimum, couldn't you just like infinitely decrease it? Like, shouldn't you say like if we're within a certain amount, then you stop moving?
So you could just do this gradient descent step forever, right? So I say like our stopping criteria must be when the slope is zero, if the slope of our gradient is zero and that our second derivative is non-negative, but in practice, you won't get there, right? Like you probably won't land perfectly on the actual true minimum. And so what we typically want to do is just set a stopping criteria. Say that, hey, if the gradient is less than some amount, right, that means my slope is like really shallow, I'm good enough. Like I should just stop here. But yes, absolutely. So in practice, you can do a lot of stuff for step size. There are varying efficiencies of strategies there, depending, and it's a trade-off, of course, between how optimal you want to be and how quick you want to just get kind of close enough. And so can we really accomplish this with simple gradient descents like we're talking about? Sure, as long as we've set up our problem to be this kind of convex optimization problem, then we can do that. But of course, like it's just an optimization problem. So saying like that gradient descent is capable of solving it is only really part of the equation, right? Like we have to actually make sure that the problem is set up for gradient descent. And that's one of those trade-offs again, where like the more time and the more specificity that we use in setting up our problem, usually the less work we have to do to actually solve it, because we put a lot of work into that initial that initial part. Okay, so let's move on to actually talking about how this maps to mobile robots, because that's what we're dealing with. And so for this week's lab, we're going to be using inverse kinematics combined with feedback control to get a mobile robot to essentially just go where we want. So we're not going to be using epoch this week. We're going to be using a mobile manipulator called Tiago. So epoch, I think, retails for a couple $100. Tiago retails for somewhere north of $100,000. Definitely a much cooler robot to interact with. But the idea is generally the same, because the mobile base is going to be a similar differential drive concept to what we've been using already. We also have a mobile manipulator robot in my research lab. That one retails for about 200K. They're very expensive, but they're very cool to use. And so the important thing to note here is that the stuff that we're learning on, say, the toy platform is the exact same stuff that you will be applying if you were using one of these fully featured or really expensive fancy ones. So like the concepts don't actually change at all. Just the cost of breaking something when it runs into a wall. So for this lab, we're going to need to remember, right, what our kinematics equations look like for the mobile robot. So here, again, we have the diameter between my robot's wheels. And then I have the amount that each wheel has moved. So that is phi. So phi is the amount of rotation that the motor's had. And then lowercase r is the radius. In our case, we actually empirically measured this, right? So like we know how many meters our wheel is going to move at maximum speed over a given time frame. So same assumptions are going to apply when we actually implement this ourselves. But we were able to use that, that math to figure out, here's our robot's displacement along this x.r vector, and here's our robot's rotational displacement, right? So in how it's rotating about the axis coming outside of the screen. So if we take these forward kinematics equations, right, we can set this up. So this is the same thing that we've been looking at for the past couple of weeks. Right, so the x, y, and theta changes in my inertial frame are the rotation matrix multiplied by my x, y, and theta displacements. And we can rewrite this, right? So we can say that, so we'll use psi here as my robot's pose. So the change in my robot's pose in the inertial frame, right? So my external kind of like world map frame is equal to this transform multiplied by the change in my robot's local frame. Right, so from my robot's perspective, I go through this transform, and then I get the change from my global perspective. So if I wanted to reverse this, right, if I wanted to figure out what the change in my robot's frame should be, given some change in my inertial frame, I need to move this transform to the other side. How do I do that? How do I move this transform to the other side, given that it's a matrix here?
Multiply it by its inverse?
Multiply it by its inverse. So I just left multiply by t inverse of theta, right? So this is t of theta. So left multiply by t inverse of theta. These two things cancel out. And so now I can get the change in my robot's position. And remember, my robot's position is parameterized by these wheel motions. So I can get that as a function of the change that I want to see in my world frame. So again, if I wanted to have my robot move 2 units along the x-axis in my inertial frame, then I just plug in 2, 0, 0, and I can figure out, like, so 2, 0, 0, multiply it by this inverse transform here, and that's going to tell me values for my phi L and my phi R, right? That's going to tell me how much my my robot wheels have to move in order to affect that change. So this is a rotation. So fortunately, our inverse is just the transpose. And with that, we can get we can solve for inverse kinematics for non-holonomic mobile robots. So here we have our forward kinematics equations, right? So we have x dot r, y dot r, and theta dot. So the change in my robot's, from my robot's perspective as a function of wheel speed. And I've done the algebra for you, so you don't have to. And here are my inverse kinematics equations. So the amount that I should change my left wheel position, right? So the amount I should rotate my left wheel is going to be equal to my forward displacement minus my angular displacement multiplied by my axis length, my diameter, divided by 2, all divided by my wheel radius. And likewise for this phi dot r, so that's how much I turn my right wheel. So using this, I'm able to express how much I should turn my wheels, right? So the left side, in terms of how far forward I want my robot to go and how far rotation I want my robot to go. So now we're going to have to deal with a whole bunch of complexity that arises from that equation, right? So there are some competing factors here, right? Because I only have these two joints that I can manipulate, right? I have two mechanical degrees of freedom, but I have a couple of different things that I'm going to have to balance between, right? So we can maybe work through a couple of quick examples for this. So let's say I didn't want my robot to move forward at all. I wanted it to stay in place. So if that's the case, then x dot r is 0, right? Because there's no displacement for the robot along the forward part of the robot. And I wanted to rotate some positive amount. So I want to go counterclockwise. So in that case, my phi dot or my theta dot is going to be positive. And then d over 2 over r, these are all the same. So I don't have to really worry about those right now. So if I have a positive change in theta, so I rotate counterclockwise, then phi dot r is positive, right? So I turn my right wheel forward, and phi dot L is negative. I turn my left wheel backwards. And if I'm going to turn them forward and backwards the same amount with respect to each other. So that kind of holds true, right? My robot will then rotate in place. So I would encourage you anytime you see equations like this to kind of run through a couple of examples in your head just to make sure that it's like clicking properly. And likewise, if I wanted my robot to move forward, but not to rotate at all, then I have a positive x dot r, and I have a 0 for my theta dot. And so I'm going to set my phi L and my phi r to the same amount. And so my robot will move forward and not rotate at all. Okay, does anybody see any challenges with these equations or any like problems that might come up before we actually unveil some of them officially?
It looks hard to just change y.
Well, so yeah, so we can't really, so if we wanted to just change y dot r, right, we can't because the robot can't slide left or right. So remember, x dot r is the axis coming out of the front of the robot. Y dot r is the axis coming out of the left side of the robot. So yeah, we can never change y dot r. So one of the challenges, so yeah, so in chat, somebody just messaged to me that like, what if x dot r is really big? Then it probably doesn't even matter what my theta dot is, right? Because if I say that like x dot r is 1,000,000, and then my theta is like pi over 2, the x dot r is going to absolutely dominate this equation. And so now I'm still kind of stuck, right? Like I don't know how to rotate my wheels to actually, get that to work. Like the order that I rotate my wheels, of course, still matters. Because if I do just the left wheel and then just the right wheel, that's going to be different than if I do both of them at the same time. But also we're talking about a time interval, right? So how long are we talking about in order for me to actually be able to execute these rotations? Because usually I'm not going to be able to like just get a value of phi L and phi r and then just rotate my wheels until one of them runs out of rotations to do and then I keep doing the other one. So recap, x dot r is essentially how far forward I want my robot to go, right? So the displacement of my robot. And then theta dot is how much I want it to turn. So let's go to the next slide and make this graphical again. So here I have my current pose of the robot. So the robot is facing down this way. And so that's why the xr is coming out of the front of the robot, right? Because if I move forward, then I'm moving it along this vector here. And I'm going to have some goalpost that is up here, right? So I want my robot to be up at this position, facing in this direction. And so in order to do this, right, like I can try to figure out some inverse kinematics solution for this xy theta relative to my current xy theta. But there are 3 different sources of error that I'm going to have to deal with in order to minimize, like set to 0, in order to actually come up with this solution. So the first source of error is this angle alpha. So this angle alpha is how far I have to turn my robot so that I'm pointing at my goal position. And so we call that the bearing error. So if I reduce my bearing error to 0, then I am facing the point that I wanted to get to. Once my bearing error is 0, I can just drive forward. But the amount that I drive forward is rho right here, which is the distance error. So if I first minimize bearing error, then I minimize distance error, then I will have my robot on top of this point, but I won't be necessarily facing the right spot. So here is x.r in my initial configuration, right? So my robot's pointing kind of down and to the right here. And in my goal configuration, my robot's pointing up and to the left. And so our final source of error is this, so we'll call eta, or heading error. And so this is the amount that my robot has to turn, right, in order to actually face the desired final pose. So I need to solve for all 3 of these, right? So generally speaking, we want to first solve bearing and distance error, then later we're gonna have to solve for heading error, right? So get my robot at least like on top of the point or very close to the point, and then get it facing the proper direction. So in your lab tomorrow, you're going to be explicitly computing these 3 sources of error. So you will be given a current pose of the robot. You're going to maintain that current pose through odometry. And then you're going to pick a waypoint, right, or a location and a pose that you want your robot to be in, say maybe relative to where you're currently at. And then you're going to use these sources of error along with an inverse kinematics equation, the inverse kinematics equations to get your robot to that point. So let's look at each of these error terms in more detail. So can anybody tell me what my distance error equation is going to look like? So let's say I have my current pose and my goal pose, right? So each of those are going to be an x, y, and a theta. So what will distance look like?
The Euclidean distance between where you are versus where you want to go.
Exactly right. So I'll have the Euclidean distance between my current position and my goal position for my x and my y coordinate. Okay, so for my bearing error, right, to figure out what angle I need to turn in order to actually point at the goal location, I'll just give you that one. So you'll use arctan. So when you're implementing this, make sure that you're using atan2 and not just atan. So atan2 takes 2 parameters. So they'll take the y, that's the numerator here, comma the denominator. And the reason for that is because it will keep track of which quadrant you're in. If you just use atan, then you have to do a little bit more bookkeeping because you have this divisor. And you also need to make sure that you're not dividing by 0. atan2 will take care of that stuff for you. But either way, so the bearing error here, alpha, is telling you how much you need to rotate, right? So like what is that delta of your theta variable, your theta pose, to point at the place you want to go. And then lastly, for heading, heading is just going to be the angle of my goal pose minus my current angle here. Okay, so I have my 3 sources of error, but I'm not quite done yet, right? Because I know I want to minimize these things. And I know that I have these inverse kinematics equations that I can plug in, but it's not really like clear to me how I'm going to do that yet, because of course it matters how I'm turning my wheels, because, well, if I do it in the wrong order, I'm not going to end up where I want to be. So we're going to create a feedback controller. And our feedback controller is going to be in charge of 2 different things: translation and rotation. So translation is going to be a function of distance, right? So that's my x.r essentially in my inverse kinematics equations. How far do I want my robot to move? And that's going to be a function of my distance away from my goal. But likewise, I have a rotation component to that as well. So my theta dot, the amount that my robot rotates, needs to be a function of both my bearing error and my heading error, right? So I'm going to need to figure out which one do I pay attention to, right? So what if my bearing error and my heading error were pointing in the opposite direction? Well, that could cause me a problem. I don't want my robot to just freeze up. So we'll come up with some kind of strategy to regulate between bearing error and heading error. But in general, this is what my feedback controller is going to look like. I need to figure out, using my sources of error, so using these error terms, how far forward do I want my robot to go? And how much of a rotation do I want my robot to do? And so we're essentially saying my feedback controller is using these error signals to calculate a trajectory that minimizes these error signals. Okay. So let's put everything on the screen again. So now I have my update rules, so just from the previous slide, and here are my inverse kinematics equations. And so I will choose some function, right? And this is something that you and your lab group will do together, is you'll pick some way to determine what x dot should be, right? And so that gets plugged in to x dot r right here. That's how far forward you want your robot to go. And likewise, you'll pick something for your theta dot. That's a function of your bearing and your heading error to plug in for theta dot here. And that's going to tell you how much each of your wheels needs to turn in order to get to that final location. However, you can't just execute all of these rotations at once. And so what your controller is going to do, and this is one of the key pieces that you need to complete the lab, you need to essentially treat these not as absolute amounts that you have to rotate, but rather a hint, right, that pushes you in the right direction towards minimizing those error signals. So if, for example, phi dot L is twice the magnitude of phi dot R, so that means you're going to rotate your left wheel twice as much as your right wheel, then instead of actually using these phi values, because there's no way you're going to be able to rotate your wheel, let's say maybe 10 times in 32 milliseconds, right, in one time step of your simulation. So instead what you're going to do is you're going to use it as a proportional controller. You're going to say, hey, my left wheel needs to turn twice as much as my right wheel. I'll set my left wheel to max speed, and I'll set my right wheel to half that, right? So whatever the ratio there is, you're going to go that proportion of whatever you want your robot's maximum speed to be, and that's how you're going to get your robot to get from one position to another using these inverse kinematics equations, right? So you're essentially just setting up a feedback controller, and you are getting closer and closer, 32 milliseconds at a time, until you hit some kind of stopping criteria. And so the slide that I'd like to end with here, you will be solving 3 challenges in your inverse kinematics lab. You will have multiple weeks to solve these challenges. So the first one is to implement the equations for error sources, right? So your bearing, distance, and your heading error. And I encourage you to test a couple of different positions around the map to make sure that you're getting values that look reasonable. Your second challenge will be to implement a feedback controller that will get your robot from its current position to one of these goal positions that you set, right? So figure out how much your left and your right wheel need to turn, figure out the proportion with respect to each other, and then set your wheel velocities in order to actually start trending towards that goal point and figuring out a stopping criteria, right? So for when you say, hey, look, I'm close enough, I don't have to keep trying to get there. Because if you don't set a good stopping criteria, so for example, you say, I'm only at my position when my distance and heading error are 0, your robot will presumably go and kind of overshoot it and then come back, overshoot it and then come back, and just do that endlessly. And so you're going to want to have some tolerance in there. The last thing, once you get your feedback controller working to get you from one point to another point, is going to be to set this up via state machine such that your robot will now go through a bunch of different waypoints to navigate from its starting location, which is in the dining room of this house model, into the kitchen without hitting anything. And so in order for you to be able to do that, you're going to need to pick a bunch of different waypoints along the way, right? So relative to your robot's starting position to guide it to that position. So we're going to be doing that manually. So you'll get to choose those waypoint values. And then hopefully, if all goes according to plan, you can just put those into your feedback controller that's using your inverse kinematics equations, and your robot will then follow that path. And so this is lab 3 in its entirety. You will have several weeks to complete this. We will have at least 2 lab periods devoted to it. And depending on how it goes, we might do a third one. But I think that is going to be like a sufficient application of this so that everyone will understand really like how to bring all of these things together, which of course is always going to be our goal. And so with that, we are at the end of time, class time today. If you have any questions about anything, feel free to post on Piazza. We will be answering those tonight, and we'll continue to try to be pretty responsive to that. Any questions about submitting lab 2, definitely get in touch as soon as possible. And the graders, I believe, have almost finished with lab 1. And for those of you who noticed that we didn't do the quiz, don't worry about it. That was just in case we like really rolled through material too fast. So I think we can do without it this week.
Professor, could I ask you something about lab 2?
Yes, give me one moment here. Let me just stop all the screen share and recording and all that good stuff.